there is Professor Hong Tzay-Ming of National Tsinghua University. Professor Hong is our alumni. He was graduate in 1988, and then he went to UC San Diego to earn his PhD.
1982. It's okay, 88 is there.
Okay, 82. Then he went to Cambridge Lab and Sheffield University to as a postdoc. Then he came back to Taiwan at 92, right? 92, and to National Tsinghua University up to now. He's going to give us a colloquia on a very unusual topic, which is very far from our mainstream research in physics. But his outcome is so interesting that the Phys today have reported their results. So maybe I just stop here and let him to present his results. So let's welcome Professor Hong.
Can you hear me from the back?
No.
No. No. Okay. So it's very nice to be back here. So as you see, I brought a lot of real experiments. So this is like going to a sea world. So if you don't want to get wet, you should try to sit backward. So shampoo is going to sprinkle water all over. No kidding, really. Okay. So what I'm going to tell you today, these experiments were performed mainly by undergraduate. So that means you can turn off your antivirus. This is not hard. So they were mainly experiment. When I tell you any theory, I make it up. So you can attack me. In 中文，我用白的。So most of them are they are very shaky. So the main purpose of coming here, actually, I want to get input from you guys. So if you have any question, interrupt me at any time. Okay, just raise your hand. You can ask in Chinese. That's okay. Okay, so anyone know what does this picture come from? Can you guess? What is the background of this?
清明上河图.
Yeah. And so what is the background? What city is this? 汴京. So 汴京is 河南开封 nowadays. In those days, it was the capital of Beisong. So what peculiar, what interesting thing can you see in the picture? Try to be kid, to be elementary student. What interesting can you see? So you can see they have camels, right? In those days, so you don't see camels in Taipei. So it is more metropolitan than nowadays. See, so they have what? They have all kinds. This street performance, and they also have paintings. Okay, so these are scroll paintings, and you have hand scroll, hanging scroll. So that will be the subject that I'm going to talk about today. Okay, right? Okay, so. Scroll painting has been in China or in Asia, in Japan for more than 2,000 years, okay, or maybe longer. So the problem I'm going to tell you about has never been solved, okay, for 2,000 years, at least. Okay? Right. Okay, right. Okay, so try to give you some nice picture. Oh, okay. Okay, to be honest with you, yesterday I have a panic. my adrenaline tried to rise. It's getting to rise. So I try to ask myself, why am I so nervous? So I think it is not the physics part, because I have delivered this talk many times before. I think it's a joke. Because when people fall asleep, I try to tell a joke, but normally it's in Chinese. So I need to think of some joke that I can speak in, that I can deliver in English, and the audience can understand. That's very hard. I tried some joke today at lunch, but no one laughed. so now I know I'm in serious trouble. So when you see me try to search for a joke, that means I'm starting to panic. Okay. Right. Okay. So try to make the atmosphere more cordial. So let me ask you. Let me ask first. Panic. So I'm getting panic. So what's the difference between stress and tension and panic? Anyone there? Because you see in later pictures, there will be a lot of stress on papers. Okay, so stress, tension, and panic. Okay, so the joke goes something like this. Okay, I try to be short. Okay. If you don't want to laugh, it's okay. When your girlfriend get pregnant, you get stressed. Okay, but when your wife get pregnant, you start to have tension. But when both are pregnant, you get panic. All right, okay, so that's good. All right, okay, so let's start. Okay, right. So in National Palace Museum, there are a lot of good things. Right, and the answer to my topic, how do you do this? I'll postpone that to the final discussion. Okay, so we discuss how do you do that, and there are many problems they want us to solve. But today I'll just concentrate not on these. Okay, these also have problems. Let me see. Okay, for instance, for this, they have a crack. They have a crack in this, and the crack is very different from, let's say, in Mona Lisa. Okay, in Mona Lisa, you have oil painting. So the underlying physical mechanisms in oil painting is very different as in porcelain. So that's, for instance, that's one problem. Okay, okay, there are other problems, but let's forget this. Okay, is there any foreign friend from here? Do you know what this is? What's special about this? No, this is what do you call that? Walnut size. This is what do you call that?
Walnut.
Yeah, a tiny walnut shell. So they have. Okay, right. All right, let's compare. All right, so this is another book. So Chinese history has a long history. Okay. So let me see. Where is Korea? Oh, Korea. Somewhere in here. Okay. So all right. Okay. So that means there are a lot of treasures, national treasures, in the National Palace Museum. Okay, so they need a lot of help. Okay, but how physicists can sort of offer assistance, how physicists can tap into their problem. Okay, that's something that I will try to discuss at the end of this talk. But just first, just give you an example of how long our history is. Right. So the topic that I'm going to concentrate are paintings. There are two kinds of scroll paintings in National Palace Museum. For instance, you have this is called scroll, hand scroll, 手卷，不是寿司那个手卷啊，但一样的字。This is hand scroll. So hand scroll can be as long as 10 meters, as in 清明上河图, walk along the rivers in Qingming Festival. This is very long, over 10 meters. And these are hanging scrolls. Okay, and the problem that I'm going to discuss is if you look carefully, on both sides, they sort of curl outward. They'll curl up, okay? And this is not very obvious because this is probably just 1.5 meters. But if you go to National Palace Museum, they have paintings over 3 meters, and that will be very obvious, okay? So you have an up curl. Then you will ask, what's special about that? And first of all, it's ugly, okay, because it just doesn't look good. But worst of all is there will be a lot of stress. Okay, see, stress, panic, tension. Okay, so girlfriend, Remember the stress? Okay. There was a lot of stress built up in here. And in the end, just like this painting, which I get from my parents' attic, they will break because they have a lot of stress. So the paint would tend to fall off. Also the fiber would tend to tear. Okay, so that's a serious problem. Okay, so that's a problem they want us to solve. And you can imagine, this must be over 2,000 years, this problem. Because as long as you have scroll, you have this problem. Okay, so this is the problem we're going to discuss. Okay, anyone, problem? And to convince you that this is a very old, so let me give you some example. Okay, so this is propaganda. Okay, so that's right. So when you show this, you look like you are very cultivated, right? So this is ancient, sort of ancient Chinese. So you can see, for instance, this Wa Huan. So they have also discussed, and they have also proposals. So for instance, some says, it's a paste. What do they mean paste? Because in Chinese painting, we paint on rice papers or silk. So they are very easy to tell. So in order to protect this, you have mounting papers, 装裱. You have tougher papers on the back. So in China, we have 3 layers of mounting paper. In Korea or in Japan, I think it's 2 layers of mounting. Okay? So in order to protect your painting, you need to have these mounting papers. Because they have several layers, so you need to have paste, 浆糊, to paste it, okay? So some, in old times, some workers, they believe the paste, the quality of the paste, and how uniform they are posed, that would determine how serious this problem will be. So this is, for instance, the first one. It tells you how the secret recipe, okay? And sometimes they will emphasize on the skill of the masters, okay? And sometimes they will emphasize on humidity of your room, for instance, like this, okay? You can read, so. And sometimes they will emphasize on the weather. So all kinds of factors. So they think this problem is very serious, very complicated, very complicated. Okay, so that's the point of view from the National Palace Museum. Okay, they said this problem is just too complicated, so there's no way you can solve it. Okay, so now we're physicists, so let's see. That's it.
Now you can show us the point of view of physics today.
Okay, sorry, that's propaganda. Okay, so blah blah blah. Anyway, I'll translate them. I mean, so it doesn't matter. Okay.
Okay.
Right. Okay. Right. So that's the paper. So, right. So that's a traditional view for 2,000 years. They think it's just too complicated. Okay. Right. So this problem is in collaboration with the National Palace Museum. So that's our collaborator. And that's the only student that I can find. That's Tzay-Ming Hong. So he's now in Chicago. Right. Okay, so that's my outline. So not to waste time. So let's first go to the discussion. Right. So why the National Palace Museum would sort of seek our help? The problem is the reason is because in the past 3 years we've been working on crumpling. Okay, so I'll tell you why crumpling. So everyone knows how to crumple, right? So when you write, you get a rejection letters, okay, or you write a very bad report, you get C or you get over 60%. Oh shit, you do this. Okay, so that's crumple. Okay, so let's start experiment to keep you awake. So there are a lot of physics that even I do not understand. I only know some phenomena, so I'll share with you the phenomenon and then you try to answer, okay? So the first puzzle that we try to answer in this experiment is, probably most of you have heard that if you're given a piece of paper, no matter how large, you can only fold it 7 times. Anyone heard about that? 7 times or 8 times. So for instance, this is a aluminum foil. Okay, so I'll let Professor Hu, okay, try to fold it. Let's see how many times he can. That means he's still very young. Okay, so that's one fold. So that's folding. Okay, you try to fold this. So that's folding. 折，来回折，规则的折。And this is 揉. So please just roll it up real hard. This is your enemy. Okay? 对，来回折，对，就来回。Yeah， 这样看几折。Four fold. 3, 4. Yeah, he's trying real hard. 5, 6. Right. Almost there. 7. So let's see if we can get 8. So you see, it's hard. It's hard. Okay.
It's not impossible.
Yeah, but it's very hard. Right. Okay. So now, anyone can tell me the reason. As a physicist, what is the origin of the resistance? Why it's very hard to get the 8-fold? What is keeping you from doing the 8-fold?
Tension.
Tension. And how about this? I mean, it's really hard. I mean, you can feel it. It's really hard. Okay? And you can see. So now the question is why? You can see the depth under the water is about 3 to 7. So that means the density of this crumpled board is about 3/10, 0.3 of the water density. That means it is about over 70% vacant. But you try to compress it, you can't. I mean, it's real damn hard. Sorry, it's hard. Okay, it's hard. Okay. Okay, so now the first question is, what happened? What is the mechanism for this board? I mean, why can it be so hard, even when it's over 70% vacant? Okay, so that's the first question we try to answer. Okay, and the second question is, although this guy is so vacant, is the physical mechanism of the resistance of these two guys the same? Okay, so that I'll try to convince you in the first quarter of the talk that they are. Okay, they are same physical mechanism. Okay. Okay, so I get your attention. Right. So at the beginning of this talk, so this experiment was done by a junior, 大三学生. Okay. So the way we do this is first we try to understand how does crumpling, how does the size respond to force. Okay. So you say, it's idiot. Of course, the larger the force, the smaller the radius. Everyone knows. Okay, but I try to be quantitative. Okay, I try to quantitative. So this is because I was told that this talk will be mainly for experimentalists. So we try to put on some photo that maybe look like an experimentalist. Okay, we will not go into detail, but we have equipment, so we look like we are experimentalists. And these are our experiments. So, right, so, okay, yeah, right. Okay, so what is this? So this is, if you cut this in half, so this is like 高丽菜. If you cut it in half, this is what you see. This is the big circle. Okay, so you see all sort of cross sections. Okay, and you can imagine the numbers of lines would increase when you crumple the board. 越来越皱，它就越来越多线。Okay, now I'll do a second experiment. Okay, I only have 2 hands, so you have. Imagine when I crumple this to this extent when I cut it in half. So this is probably what I see, okay? Okay. But when I try to crumble it further, you can expect this thing would denser, right? Because the board gets smaller. Furthermore, there will be more chopsticks, and there will be more sticks, right? Because it's, so let me demonstrate. So you have two effects. First, you have more lines. Second, okay, so what do you see?
Line.
You get ordering. See? So that means high density would spontaneously promote ordering. So that's what this red box means, tells you. When you try to crumble it, the layer will start to line up such that it looks like this, all patches. So it becomes all different patches, just like different this. They start to line up. So that's, you start to have the pregnancy, the tension. Professor Zhu says, you start to have this tension. So you got tension everywhere. And these different blocks, they sort of locked, intertwined. Okay? So it may look like a very different thing. One would sink, the other would float. But we try to convince you that the underlying, the mechanism of the resistance, actually, they share the same origin. Okay? Question?
Is this against the second law of
No,
thermodynamics?
it's not.
You get order.
No. So, second law says you try to increase the entropy. So in this case, there are two entropy. The first entropy is the center of mass trying to move. And the second entropy is they try to rotate. So when the density gets high, in order to get the overall maximum density, they try to minimize, try to sacrifice the rotational in order to increase the translational entropy. Okay? Okay, to convince you, this is not my theory, this is my own saga. You can look up. if you don't believe me, then try Feynman. No, I'm kidding. Really, it's my own saga. Okay, so that means you try to, you have two sources of entropy. You try to minimize one to increase the other, and it's intuitive because I just demonstrated to you. Okay, this is like when we try to play poker game. 玩完扑克牌，你要收的时候就是这样子。You just put it together automatically. They will start to line up. Okay, it's intuitive. I just put it in words. Okay, question? Okay, so that's the first lesson we learned from this.
What's the relation between this crumpling and the limit of the force?
Okay, so that's the second slide. So that here you are. So this is the force. This is the radius. The larger the force, the smaller the radius. So this line sort of decreases monotonically. And what's special about this is there is about 1 to 1.5 order of magnitude. It looks like a power law. Okay. It looks like a power law. So what do I mean by power law? That says if you plot x, y as a full log scale, log y, log z, you can see this is log scale. It becomes a straight line. Okay, so if you don't know what I'm talking about, I'll show you in the next slide. But to answer Hui Su's question, there's about 1 to 2 order of magnitude, they behave power law. And power law is very fancy, very popular. Okay, in many areas you get power law. So that means you can fit this y as a function of x just by one term. Okay, let me show you first. Just like this. Earthquake in Taiwan and Korea, a lot of earthquake. So this is a very famous 瑞士规则是第二个 Richard. Okay, this is in the early 19th century. They found that the magnitude of earthquake and how many times, how frequent they occur is also a decreasing function, right? This is 无感地震，每天都在发生, so it's a lot of them, and that's a real big earthquake. And there are very few. is monotonic, but you can fit this by a simple power law just like that, with an exponent between 1 and 1.5 to 2. So that's the power law. No one understands why. Why you can fit this just by a single term, okay? Okay, so that's called power law. And in our case, we also found that there's a region that also behaves like a power law, okay? And let me see, do I want to tell you the, okay, right, okay, so that's that. So then, question?
Can
Do you want to go?
fit a function to it? What do you mean by power law?
Power law
What
means
kind of,
R goes like 1 over f to a simple power, just one term.
How do you fit it?
Oh,
How do you prove?
Yeah, because if this is a power law, then for log term, it will become a straight line. And the slope will be your x exponent. So that's, okay. I'll tell you more interesting power law later, but this is the power law, okay? And the cartoon on the top, that's another physics, which I think is easy to understand. So that means they have different mechanical behavior. So in this part, it's similar to that, except I plot pressure instead of force. Okay, so that's similar. And instead of radius, I plot the density. Okay, so it's similar. And there will be a 3 regime, 3 different mechanical behavior. And we associate them to different structure. Okay, so let me explain the physics. So this is very common in soft matter physics, in which the mechanical behavior is related to the structure. A structure change would usually give you a different mechanical behavior. So a very famous example is this. Just after the Industrial Revolution, 在英国，这工业大革命 the newspaper or the clothes industry, they try to print as many newspaper, as many clothes as they can because it's a machine. Machine can work 24 hours, can work 7 days a week, right? So the more they print, the more money they can make, okay? In those days, they found a problem. The company or the machine usually will blow up and cause a lot of deaths, okay? When they try to crank up the speed, eventually the machine will explode. And that's called, very famous, if you look up the Wikipedia, it's called shear thickening. That means when you try to shield the paint, so it could be a newspaper paint, or it could be the pigment to paint your clothes. It's a colloidal, okay? 有点像沙拉酱，里面有一些悬浮液 colloidal system. They have viscosity. So if you measure them, they have viscosity. But in this colloidal system, the viscosity would change with respect to how fast you shear it. So this is shear stress, shear rate. When you shear it slowly, it's a constant. But when you increase, when you try to push the machine faster, you get a very good regime in which the viscosity sort of drop. So you say, it's good because your electricity bill falls off. That's called shear thinning. When you try to, if you're very greedy, you try to crank it up in the machine, it starts to shoot up. Okay, viscosity gets up, so that means the machine would become very viscous. So there will be a lot of heat. So eventually it just explodes. Okay, so that's a very famous example in paint. And in this case, people have understand that the reason is because there are structure change. Viscosity is the mechanical behavior. Okay, so what is the physics behind it? People believe that